Good afternoon, guys. I'm here to talk about encrypted traffic analytics. So I'm sure all of you must have seen Chuck's keynote yesterday. And among the three things that he talked about, he talked about DNA Center, he talked about the Catalyst 9300, and then he talked about encrypted traffic analytics. So I'm here to talk about encrypted traffic analytics in a lot more detail today. And I'm excited about this topic because I'm going to be talking about a solution to a problem that many in the industry thought was not solvable, right? How do you detect threats in encrypted traffic without decryption? And that's the key, right? How do we detect encrypted traffic, malware and encrypted traffic without decryption? And that's really the innovation in this solution. And if you look at we've had a lot of ideological debates about whether true network security is indeed possible without compromising on the end user privacy. And I'm here to tell you that we've solved that problem, and we'll see how we've done that, right? Now, here's what I'm going to do. There's a lot of material to cover, so I'm actually going to be, this is how I'm going to be spending the time. I'm going to be talking about the specific problems really quick, right, that we're going to be going after. And then I'm going to be talking about the research, which I'm sure is what you guys are all interested in, what we've really done from a research perspective to be able to solve this problem. And then I'll spend some time talking about the product that we're actually launching, because there's some difference between the research that we did and then the product that we're really launching. And I want to do a demo here, and finally, take it home with the key takeaways from this session, right? So I'm Saravanan Radhakrishnan, by the way. I'm a distinguished engineer in the enterprise networking group, and I've worked on a number of security-focused innovations and initiatives over the last 18 years, and there's none that I'm prouder of than encrypted traffic analytics, because I believe that, and I'm sure you guys will agree, that this really changes the industry in a significant way, right? So what are the specific problems? I'm going to be talking about three trends here, right? So specifically, one is, and we'll keep this short, but you guys are aware of the fact that the volume of encrypted traffic is increasing significantly year over year, right? Between 2015 and 16, we saw that this kind of exploded from 21% to 40% of all web traffic. That's a 90% year over year increase, right? And then, this is expected to be almost like 80% of all web traffic by 2019. And a lot of the sites that we actually, access on a daily basis, like YouTube and Google, already encrypt a significant percentage of their traffic, right? Now, the enterprises are also adopting that for good reasons, because, as they do more of their business online, they want to be able to protect their data in motion. And so encryption, kind of offers them a nice way to, do that, because now they have a secure and a more, safer way to be able to do their business online. So all of that is good, and we expect, that to increase, right? Now, unfortunately, the IT budget that is actually being spent on this hasn't kept up, and there are several reasons for that. We'll talk about that in a bit. But, that's one trend that we've observed. The second trend is that while, encryption, unfortunately, is a double-edged sword, right? Like, there are people who are using it for good reasons, but then the threat actors that are starting to use this for other reasons, right? And so what we're starting to see is that a significant percentage of malware is now starting to leverage, encryption to evade detection, right? Now, almost 40% of malware that we, did in a study actually is starting to, evaded detection by using some form of, encryption, right? Now, and if you look at the customers that we spoke to, almost 80%, 70% of customers are really concerned about encrypted traffic opening up new threat vectors, and there's a good reason for that. There are several new threat vectors that are specifically attributed to encrypted traffic, right? Like you could have your laptops right here, which could be and you could be browsing, right? And you could be using HTTPS sessions. What you wouldn't know is that you're probably communicating with a compromised server, and that could be downloading malware to your device, and you wouldn't know anything about it, right? And similarly, you could have a malware that's communicating with its command and control server, something like what happened with the ransomware attack that happened recently, right? The way that WannaCry was communicating with its command and control server was through an encrypted channel, right? So all of that could be happening at this very minute from your laptops, and you wouldn't even know about it, right? And that's the second trend that we've observed. And then one other thing that most of you, and this is kind of an old trend, right? So the fact is that most of the enterprises actually are now moving towards BYOD and IoT. That's significant. You saw Chuck talk about 3.1 billion devices in the enterprise today, and by the time I finish this talk, if it was 2019, it will be like 500,000 new IoT devices that would have been connected in 30 minutes, right? Oh. So that's really the kind of scale that we're looking at, and so the impact of an attack is significant. I mean, we're talking about a lot of enterprises that have already been compromised, and the real challenge is that we don't have enough visibility to be able to detect this as quickly as we can, because the industry average right now is about 200 days to be able to detect a data breach, and another 60 days to be able to fix that. And that's really the problem, right? We got to get those issues identified as quickly as we can. And so what's the security posture that we really want to be able to take? And one of the things that Sean talked about in the previous session was about software-defined access. Now that actually helps us to reduce the surface area of the attack, right? By making sure that the lights are not able to talk to the printers and the users, for example. So if a light is impacted, only the lights stay impacted, right? So that's good. Now the second thing we got to look at is how do we actually detect as quickly as we can. That's really going to be the focus of this topic, and we're going to be looking at encrypted traffic analytics in that context. And then finally, how do we actually tie this back to a policy engine like ICE to be able to take specific actions and quarantine the user or what have you, right? So that's what we're going to be focusing on in this session. Now, one of the easy ways to do this is, we can actually decrypt the traffic. A lot of firewalls do that today. They decrypt the traffic, they look into the packets, look at patterns and so on. But that's, there are problems with that, right? One is, with the exploding volume of encrypted traffic, if you start relying on the firewalls to decrypt, you got to be building like beefier, firewalls all the time, and you're not going to be able to keep up with that, right? And the second thing is that it also kind of violates on the privacy requirements from an end user perspective, right? So that's really the challenge that we're going to be looking at. And so, what we really want to do is that, can we really look at the body language of a person and identify what he's thinking? So similarly, can we look at sort of like the body language of packets and kind of infer, if it is malicious or if it is benign? And that's really what encrypted traffic analytics makes possible, right? So we're specifically going after two use cases. One is detection of malware and encrypted traffic, and the second is the cryptographic compliance. Because as a lot of enterprises are embracing encryption, what we've noticed is that the budget doesn't increase for that, right? So the real problem is that they're not really checking if their cipher sheets are secure. Is it the right thing that right algorithms are in place and so on, right? So that's the other problem that we intend to solve with this. Okay, so that's really the precursor for this, and let's move on to the real research that went onto this. So what's the challenge that we had with us, in front of us when we started this? We have a lot of benign TLS communications that originate from our laptops. Like I said, the YouTubes and the Googles and what have you. All of those are already using encrypted communication. Now, malware uses a similar pattern, right? But in this case, to communicate with the command and control server, to get commands from it, and to be able to sort of exfiltrate data as well, right? So how do we actually differentiate between these two? And that's where I think what we really wanted to do was we wanted to be able to fingerprint malware, right? Just like we have features like we have a thumbprints and iris scans that kind of helps. Those are the features that help uniquely identify a person. We wanted to come up with a unique fingerprint that will help us in identifying malware, right? And that's really the basis for the research that we did. So what we really wanted to do was we wanted to build tools that will help us in fingerprinting encrypted malware communications. And to that extent, we kind of identified some data features that we believe would actually be useful, and we observed those data features across millions and literally millions of encrypted malware as well as encrypted benign communications, right? And what was a source of malware communication in this case? It's Cisco's threat grid, right? Because what you guys are aware of threat grid. What customers generally do is that they generally upload a lot of files to threat grid to have it. It's a sandbox environment which will actually explore that file and actually see if it's a malware or not. It's integrated with Cisco's AMP. So AMP runs on the endpoints, it runs on the firewalls. So anytime it sees a new file, it's actually going to send it to threat grid for analysis. So threat grid actually serves as like a really big repository of known malware PCAPs, right? Now on a daily basis, threat grid typically convicts about like 10,000 new flows. So imagine that's the database that we have, right? Now that was one of the sources of information for us. And the second was, we had benign traffic that we collected from our DMZs, right? So we analyzed these data features across all of these, millions of flows. And what we, identified was some of our core insights, right? Things like, the typical benign applications, the enterprise applications, they tend to use cipher suites, which are more up to date. While, if you look at the malware communications, they tend to use, more, sort of older or weaker, algorithms, right? So that's led us to build some, state-of-the-art machine learning classifiers which we kind of, used, which we tested with the flows that we really collected, right? And so in that research, what we were able to observe was that we were able to identify 99%, actually it's over 99% of malware, with a very high degree of efficacy, and then the false detection rate, and that's that, the benign traffic that we captured, that helped us in reducing the false positive rate. So, it was really of the order of like a few 0.002% or something, right? And again, the key is this, right? How do we measure this? We got samples from ThreatGrid, and we kind of, observed some data features. We built the machine learning classifiers, and we tested it on the data that we collected, right? And so we were, right 99% of the time in being able to, identify the malware, right? And so, I want to make sure that the terminology is right, because I don't want to say that, hey, we can capture like 99% of all the malwares that are out there in the internet. That's not what we're really going to be able to do, right? So from the samples that are known to us, we will really be able to identify them based on these data features with a very high degree of efficacy, right? So that was really like the fundamental building block for this work, right? Now, key question is, what are those features? How do we actually identify them, right? And that's really where the interesting piece is, right? So the first data feature is really the sequence of packet lengths and the time interval between the packets. And why is that unique? So if you look at a typical malware, the way it operates is that it's actually going to be, communicating with the command and control server, and then it's going to be writing something to the disk, and then it's going to be, communicating something to the command and control server, and again, it's going to be writing something to the disk. Now, if I were the router or the switch in the middle, and if I'm looking at this pattern from the application, what am I going to see? I'm going to see a sequence of packet lengths from a specific application, and there's going to be like a delay between, or a time interval between these packets, right? And that's really, what we figured was unique for malware, and in some cases even applications, right? So the point is that, the sequence of packet lengths and the time interval between the packet is one data feature that helps us in uniquely fingerprinting malware. But that's not sufficient. We also look at additional parameters, right? So that's one of these things. The second thing that we look at is the initial data packet. So if you look at a typical HTTPS connection that you open, right? Now, the initial TLS protocol exchanges happens in clear text, right? And that actually gives us a lot of information about the identity of that application that's generating this flow, right? So, the initial data packet typically is like the client hello message that goes from the TLS client to the TLS server. Now, what that typically has are things like the list of cipher suites that are offered to the server, and say that, here are the cipher suites that I offer in the order of preference, and then pick what you're comfortable with, and then the server will actually respond back saying that, here's the cipher suite that I want you to pick, and so on, right? Now, what we believe is that the list of cipher suites offered and the subgroups that are offered, and in combination with there's one more field called as the list of extensions, we believe that actually gives us discriminatory information about the specific TLS library that is being leveraged by the application, right? So that is one of the other things that we actually looked at. Now, these two in combination is what helps us in actually being able to identify either malware or benign traffic with a reasonably, as you saw, with a very good degree of efficacy, right? Now, I wanted to show this with a real malware, right? So how it really works, right? Now, I wanted to do a demo with one of your laptops. What Bestafera is it steals your online banking information, and we're keylogging, and it'll send it to a command and control server. In this case, it could be me, right? But I'm just kidding. So I didn't want to do a real demo of that. But what Bestafera really does is that it's an online, it's really a keylogging kind of and data exfiltration malware, which steals the banking credentials. Now, this is the interesting part. If you look at this picture, right? So this is the sequence of packet lengths and times that I have for some benign traffic, which is in this case Google, and then we have a Bestafera, right? So if you look at Google, what's interesting is that anything that is above the horizontal line is anything that's above that is traffic that goes from the client to the server. Anything that's below that is traffic that goes from the server to the client, right? So what do we do in a typical Google search? I type in a string and I do an enter, right? So when I type in a string, that's basically what you see. There is a small, that's the packet length, right? And then you see a whole bunch of responses back from Google saying that here's the, here are all the results, right? Now then, what you do is you tend to change your search string, and then Google does its bit by trying to, think what you think, and then it tries to autocomplete, right? And so that's basically what you see here. It tries to autocomplete, and once it's done, you again see a whole bunch of data coming back from Google, right? So this is like a typical benign search, benign TLS communication. Now, if you look at Bestafera, what you will see is that you actually see a whole bunch of information that is actually going from the client to the server, and that's not common, right? I mean, it's not always bad, because sometimes you could actually be uploading some files to, let's say, Dropbox or Box or whatever it is, or Google Docs, and and by the way, that's also something that you got to be looking out for, because you could actually have like an insider who's actually sending data illegally to one of these Box folders, and that is something that we need to be able to capture as well. But in general, if you look at it, this kind of pattern is not normal, right? But is that enough to be able to convict this? Probably not. We need more information, right? And that's where the second field, which is the TLS client fingerprinting part, comes in. So what you'd see is that, we have in general, right? So the way this works is that some of these applications, most of the applications, right, they use standard TLS libraries. I mean, like we have libraries like Boring SSL, NSS, and OpenSSL. These are the most common libraries that are out there, which makes it very easy for app developers as well as malware developers to leverage this encryption, right? Because they don't have to now go about developing their own ways to do TLS. It's all there. They just simply have to include that library and do what they want to do, right? What we believe is that from the data that we've seen, there is a pretty unique fingerprint in the way for every SSL library. Right, for the specific TLS library, that in itself has a unique fingerprint. But then, what's more unique is the way the applications use them, because some applications, they change the defaults. They say, hey, like for example, your web browsers, they'll want more heavyweight encryption algorithms as opposed to your mobiles, which are probably going to be asking for more efficient, encryption algorithms, right? So the point is that, each of these applications, they change some of the parameters of the library in a different way to suit their needs, right? And what we've noticed with Bestafera is that it simply uses the default. It just simply uses the default, parameters of OpenSSL, right? So when we combine the SPLT, the sequence of packet lengths and times, with this information, now that's basically what gives us a very high degree of confidence in actually being able to say that this is indeed a malware and this is indeed Bestafera, right? Because the combination of these two is what we use to be able to uniquely fingerprint that specific malware, right? So in summary, like these two parameters, like the SPLT gives us information about the behavioral profile of the user of the application, and then the cipher suites information from the initial data packet is basically going to give us information about this library that the application is using. And this combination, we found based on our data so far, has been pretty spot on in being able to identify malware in encrypted communications. So that's the fundamental research, and I can now go into the products, but I wanted to pause here. So one of the other things is that we kind of build all of this into a machine learning classifier. We use a deep random forest search. We kind of feed that into the machine learning classifier, into the machine learning algorithms, and that trains the classifiers, which we then tested with our whole bunch of data that we've been collecting ever since we started this project. And it's holding up, by the way.
So would it be fair to say that the sequence of packet length and times is machine learned based on normal patterns that are constantly going through the network, and the TLS fingerprinting is signature based?
The TLS fingerprint, when you say signature based, so in effect, the SPLT will actually help us in identifying some of the benign traffic as well, because the benign, like that's probably what you were asking, right? So if you generally see more traffic from the server to the client, you can actually be fairly certain that this is going to be like benign traffic, right? But then when it comes to the malware, even the way the SPLT looks for malware, like that in itself is kind of unique, right? So you have like a specific set of packets, and then there'll be some time interval, and all of these are parameters that go into the machine learning classifier, right? And then from the TLS fields, what we've observed is that there are 176 unique cipher suites and about 21 unique extensions that we've seen. And that's basically what is fed into like the machine learning algorithms, because that's basically what we've noticed based on all the data, the captures that we've seen so far, right? And again, that's like millions of them, right?
But that piece is the TLS fingerprinting.
That's the TLS fingerprinting.
Okay, and the piece that is finding the anomalous traffic, that's not looking for a signature saying, I know what Bestafera looks like.
No.
It's saying normal traffic looks like this and this isn't normal based on a learned pattern.
That is correct.
So a little of each.
Exactly. That's
Thank
correct. Yep. Right. Only one of them will actually give us to some degree, right? And we've measured and by the way, we're really confident about this, which is why, if you go out there and search for, papers on this, we've already published a whole bunch of papers on this, and there's also an open source tool named Joy, which is on GitHub. You can actually, download that and see what we're doing. So we're very confident about what we've done, and we're also open to, kind of partnering with folks. So to that extent, you can actually go out and, do this search on Google. You'll be able to see a whole bunch of information that we already have out there on this. And we've made these presentations to, FlowCons and SecCons and, what have you, right? So we've really, taken it to the industry on this one.
Cool.
Okay. So in terms of the solution, I think I'm probably running out of time, but quickly from a solution perspective, right? What we are really looking at is, we want to be able to collect the sequence of packet lengths and times and the IDP, and the network is in the best position to do that. So we're going to be, doing this on the Catalyst 9300 switch that we just launched, right? So that has the UADP 2.0 ASIC. So we are actually going to be, collecting that information. I'll just quickly go over to that. So if you look at, this is kind of built on the traditional network as a sensor architecture, but we're going to be enhancing that to, send additional information. In this case, we're going to be sending the sequence of packet lengths and times along with the, the usual net flow information to the collector, right? So that's basically the role that the 9300 plays in this. The value of the UADP 2.0 ASIC is in that we will be able to collect all of these metrics without zero impact to the throughput of the traffic, right? Because we just copy, it tells, it has the capability to say, okay, I can, from a software perspective, I can tell UADP ASIC to say, hey, send me just the first 10 packets of the flow, right? And then be done with it. It just sends the first 10 copies, right? That's it. So the actual traffic just keeps going through, and we will actually simply be able to get the required information from those 10 packets, and we're done, right? So the real traffic just keeps going through. So that's really, the value that the UADP ASIC brings to the table. And so we, add that information to NetFlow, and then we send it off to the collection agent, to the flow connectors, right? So that's basically what the Catalyst 9300 enables. And one of the other things is that once we do that, we send it to Stealthwatch. Stealthwatch provides 3 functions here. Stealthwatch is Cisco's flow collector, which is on-prem. It does 3 things in the context of ETA. One is it's actually going to be consuming the initial data packet. It's going to be parsing that, and it's actually going to be doing an audit of the network, right? So if you want to figure out in your network, how many people are using clear traffic versus encrypted traffic, and how many people are using, very weak cipher suites and so on. That's actually going to be like a pretty neat way to do that, right? So Stealthwatch does that. It also sends the required information to a cloud portal, which is going to be a cognitive analytics, software stack that runs, in a data center, in a protected data center. So that's basically, where, we're going to be doing all the machine learning, and that is the function. And that, by the way, that's again a Cisco acquisition that we did a few years ago. We already have a lot of, malware that it already detects. What, this helps in is being able to detect encrypted malware, and it also helps improve the efficacy of their existing systems as well, right? So that's basically, the product that's actually going to get enhanced as part of this offering, right? So Stealthwatch does the cryptographic audit piece, and then cognitive will actually do the detection of the encrypted traffic. But then all of this is actually going to be visible on one pane of glass, which is going to be the Stealthwatch management console. So everything is actually going to be visible on that console, right? So that's basically what we're going to be bringing to we're going to be launching. We're launching in Cisco Live this time. So this is the cognitive analytics piece, and I don't think I'll have time. I really want to see if I can do a quick demo for you guys. But this is basically what cognitive analytics brings to the table. I'll quickly. Well, actually, let me just go over to the, so if you look at this, right, what we have here is that this is what the Stealthwatch management console looks like. So you'll actually be able to see the different encryption algorithms. This is like, you can actually say, you can actually filter it out, and you can also see that a lot of streams are actually not encrypted at all. Like some of them have none, some of them have a specific TLS version, and so on. So that's basically what Stealthwatch actually brings to the table. And we'll also be able to do the encrypted malware detection part. I'm not going to be able to do that on this laptop, but let me just do that video, and then I'll send it off to you guys in terms of like how we. I have a separate video which shows how we can actually do the encrypted traffic analysis piece on cognitive threat analytics. I'll just send that out separately. But that's basically what we're doing with encrypted traffic analytics. It's the research that enabled the solution, and again, a lot of it is out there in the open, so you can actually go and take a look at that material and open to questions.
Here's something that came from Twitter regarding the method that you're using to identify the malware. Bob McCouch actually said that it seems like if this method takes hold, if this is how it's going down, then the malware will just need to add salt to their transactions to throw.
Absolutely. So that's a good question, and we've got a lot of that, right? So the point is that anytime there is a new file, and if the malware operator is actually trying to, so there are different kinds of attacks, right? So if the malware operator is pretty sophisticated, right, and if he has access to like the kernel, and in a way that he tries to impact the way these packet lengths and times are influenced, are changed, then absolutely he can actually evade detection, right, even through this method. But in general, a lot of these are standard, application developers who are using the TLS libraries to do what they want to do. That's an economy, and they want to quickly do what they want to do, make some money and move on. So from that perspective, their focus is primarily going to be on, leveraging the existing libraries and, do what they are doing today, right? And that's basically what they're going to do. Now, if indeed they actually start, introducing random delays in their code, as such, this is still going to be, as if this is a file, it's still going to be uploaded to ThreatGrid by AMP or one of the customers. It's still going to be ThreatGrid is actually going to be looking into that, and it's going to be classifying that as malware, and we'll still be able to get that information back into our systems. So the point is that as they adapt, we have mechanisms in place that will help us sort of be up to date, or keep updating our signatures as well, our machine learning classifiers, to be up to date with what they're doing. So that's really the key. Yeah.
So it's the same story that it is now, right? I mean, as malware changes, we have to change our techniques to keep up with.
Right, but the point is this is automatic, right? Because we don't necessarily have to go and do any new programming, because at the end of the day, if that malware is actually going to get uploaded to ThreatGrid, we will know about it, and so we'll be able to
see it.
Yes.
Okay, cool.